right, welcome back, everybody. We just finished talking about everything first-order differential or ordinary differential equations, and we are now ready to move on to second-order equations, and specifically we're going to be looking at linear equations once again. So in this context, we are able to talk a lot more about physical phenomena and kind of broaden what we are able to model, broaden the scope of what we're able to model. And in this case, when we move up into second derivatives, we can actually start talking about accelerations relative to displacements. And this is exactly what many equations of motion are based on, right? MA equals sum of net forces, right? This is Newton's second law, right? Newton's second, kind of like Beethoven's fifth. There we go. So Newton's second law here. We are able to rewrite this in terms of a velocity, right? So the acceleration is the first derivative of the velocity of this object, and that's actually where we took our free fall example. We said m dv dt is equal to mg minus gamma v, and that was a manifestation of Newton's second law, but it only involved first derivatives. If we were going to be a little more careful in this in our analysis, we would actually go so far as to change this up a little bit and say maybe we didn't want the velocity necessarily, because we can get the velocity from a displacement. So if we solve this instead for a displacement, then this is the second derivative of the displacement on the left-hand side, and I'd still have a sum of forces on the right. And that would mean that my my equation here is now, or can be written in terms of just the displacement of the object. So naturally, we start moving into higher order equations when we start to make further relationships or draw further connections between different variables in our system. And this is the equation for free fall when we're looking at the displacement of our skydiver. So this kind of motivates the study of second order equations in I don't know, maybe kinematic sense. You could also look at second order equations when you start studying fluid dynamics, in maybe heat conduction, wave motion, Maxwell's equations for electromagnetism. All these phenomena can be modeled via second-order differential equations. Some of them as PDEs, but many of them as ODEs. So this is a good reason for us to start studying second order because, well, the world is Newton's second law is actually a really great starting point because so much depends on acceleration, and we would like to know where something is because the displacement and its velocity are going to be able to tell us just about everything we need to know about that system. So we would like to study the general system. D squared y dt squared is some function of t, y, and now it's going to be a function of dy dt as well, and you can actually see that right here. That we will, I forgot my gamma, didn't I? We will also have to include a dependence on the first derivative as well. So this is the general starting point for our second order equations. But if we're going to look at linear differential equations, that means that this function f must be linear in y and dy dt. And when we make that stipulation, a linear second-order equation must take the form as follows, so that we preserve a nice property that shows up a little bit later called superposition or linear superposition. But this is the general form for a linear second-order ODE, and it apparently has variable coefficients. The p's, q's, and g's can all be functions, they can all be constant. G could be 0 to make this a homogeneous equation, but I digress. This is our linear second order, or second order linear. Second order linear ODE. And this will be the object of study for the remainder of this section. Now, let's give ourselves a bit of a starting point. So recall, for first order linear equations, a first order linear equation would have to take the following form. Just remind ourselves, P of t, y equals, and then a g of t. Okay, so if I just drop the order of the equation, this is what we wound up with, and we have a general solution to this guy. But what happens if I get rid of the dependence on g here? So specifically, if I make this the homogeneous equation, then this will be 0 on the right-hand side. Okay, so we're getting closer. This becomes a separable differential equation, and we actually wind up with y equals e to the integral of minus p dt for a general solution. But we can go one step further. What if p is constant? So if p is constant, if p of t is just equal to some constant a, then this solution actually just becomes e to the minus at, and it would be up to some scalar multiplication. So the thing to point out here is that y prime plus ay equals 0 lends or creates or has solutions that are multiples of exponential functions, right? I'll wind up with minus a times c e to the at plus a times c e to the minus at, and sure enough, that's 0, right? So there's my first derivative will have a, yeah, that's fine. It's okay. The point is that our starting point should be to look for exponential solutions to constant coefficient equations that are homogeneous. These give very, very simple solution representatives, and it actually turns out that these are going to be the building blocks for just about any other solution that we can come up with. So let me give you an idea of where we're heading. And we begin with the constant coefficient equation. And typically, yes, even though the standard form is to put a constant 1 in front of the second derivative of y, we are going to take this form because this should remind us of Newton's second law. There's some constant times an acceleration term, right? And this is usually how your physical laws will manifest. So it's nice to have our equation in this form. And what we would like to do is find solutions where y of t is equal to, well, e to the rt. And that'll be for some r, or some constant r. Okay, and remember, the whole reason that we're doing this is because of the hint that we get from first order, that we're looking for linear combinations of a function and its derivative that sum up to 0, which means that the derivative of our solution needs to be some multiple of itself. The only function that satisfies this is the exponential function. All right, and what we're actually going for in one further step, if we go to second order equations, then not only do we get exponential solutions, we get complex exponential solutions. So sines and cosines will show up as well, allowing for periodic solutions. And we'll show exactly how that works in a later video. But for right now, suppose that we did have a solution that looked like e to the rt for some constant r. Then consider that y prime is equal to r times e to the rt. And y double prime, another application of the chain rule, will give us another factor of r out front. And we can go ahead and take these proposed solutions, or proposed derivatives here, and plug them into the differential equation. Right? So for y double prime, I'm using the r squared e to the rt. And for y prime, I'm using r e to the rt. Great. And for y, I just get to plug in e to the rt. And I would like this to be 0. Right? And it needs to be 0 for all t. So what happens if I observe that there's a constant, or there's a common factor of e to the rt between all three of these different terms? Well, then I have the ability to factor that out, and I get ar squared plus br plus c is equal to 0. Now remember, this has to be true for all t. And it turns out that the product of two functions here is only ever the 0 function if at least one of these two functions is 0. Well, it turns out that exponential functions are never 0. So I can go ahead and divide both sides of this equation by e to the rt, so that I wind up with ar squared plus br plus c equals 0. And this is what is called the auxiliary or characteristic equation. Auxiliary or characteristic equation. And this is what's going to tell us exactly which values are going to satisfy this assumption that our solution is exponential. And what the equation tells us is, because there are only ever at most two complex valued solutions to this equation, right? There's only two values of r that will make this work. You can see those in the quadratic formula, right? I can write that down. R equals minus b plus or minus b squared minus 4ac. That is the worst looking 2 ever, divided by 2a, right? So we all know our quadratic formula, and that is going to give us a pair of solutions, possibly one solution that is repeated twice, but at most two solutions here. So that tells us that there's a limit to what this r value can be, so that e to the rt is a solution. So if we were to do this for one example in particular, let's go ahead and do one example just so you can see what's going on. I'm going to go ahead and show you what happens in the following equation. Y double prime minus 4y is 0, and excuse me, I'm going to go ahead and use y of 0 is minus 3, and y prime of 0 is equal to 4. So notice I had to add on another initial condition, right? So first order gets one initial condition, second order gets two initial conditions. So let's have a look. If I were to use y equals e to the rt, well, then there's two ways I could do this. Either I can go ahead and substitute this guy in, so I'll wind up with r squared e to the rt minus 4 e to the rt is equal to 0, and I see an r squared minus 4 show up, right? But I could have done that just by jumping to my auxiliary equation right here and just use my coefficients, right? So basically everywhere where I see a derivative, I'm going to add in another factor of r. So two derivatives gets two factors of r, hence the r squared. So that means that r squared has to be 4, or r is plus or minus 2. Then what this means is that both y of t equals e to the 2t and y of t equals e to the minus 2t are solutions to the general equation. So, and I should use coefficients, I should use constants here, to the, I should say general solutions. General solutions. And just to make sure I'm making the distinction, so general to the ODE, I should say there are two different coefficients here, just so we're saying that they're not necessarily the same. Observe. The sum c1 e to the 2t plus c2 e to the minus 2t is also a solution. Why? It's because this is a linear differential equation, right? If I use a times second derivative here, this would be 4c1 e to the 2t minus 4c2e to the minus 2t. Actually, that should be a plus, yep. Plus b times first derivative now, so twice c1 to the 2t minus twice c2 to the minus 2t. And finally, c times c1 plus c2, or c1 to the 2t plus c2 to the minus 2t. If I sum these guys up, look what happens. I'll group up my to the 2t terms and show you that I have, what, 4a, well, what's a? Yeah, so a in this case, come on now, work with me, pen. A is equal to 4. No, sorry, a is equal to 1. B is equal to 0. And c is equal to minus 4. Okay, and we know that from this up here. All right, so we get 4c1 to the 2t minus 4c1 to the 2t, and 4e, or c2 to the minus 2t, and then minus another 4c2 to the minus 2t. And sure enough, that gets me the 0 that I was looking for. So this is stated most simply as linear combinations of solutions are also solutions. And we will return to this in the next section, are also solutions. And that's specifically for linear homogeneous differential equations. And again, we'll see this in the next section. But if that's the case, the sum of these guys, so y of t equals c1 to the 2t plus c2 to the minus 2t, this is the general solution of the differential equation. And we will show that this is as general as we can get, solution of the ODE. And once we have the general solution, we can start talking about initial value problems to get a particular solution. So y of 0, we know, is supposed to be -3, or is supposed to be 3. Yeah, shame on me. This should be a 3. Is that right? Yeah, I'll leave it as a -3 and see how it goes. And y prime of 0 is supposed to be 4. These are my initial conditions. So if I use y of 0, that means that c1 to the 2 times 0 plus c2 to the minus 2 times 0 needs to be -3. And if I differentiate this guy, I'll pick up factors of 2 and -2 respectively. So twice c1 to the 2 times 0 minus 2 c2 to the minus 2 times 0 should equal 4. Great. So that means that I need to solve the following system of linear equations. So c1 plus c2 is -3, and 2c1 minus 2c2 needs to be 4. Okay, and solving this, right, if I multiply this guy by 2, I get twice c1 plus twice c2 is -6, and I can either add or subtract that from this equation, from the second equation. So if I subtract here, I'll wind up with, so subtraction will give me a 4c2 equals -10. And that would mean c2 is equal to a -5/2. And if I added the two equations together instead, I would get 4c1, not c2. 4c1 is equal to -2, so c1 would be equal to -1/2. And then we wind up with a particular solution that takes the form -1/2 to the 2t minus, not 3/2, but 5/2 to the -2, and that would solve the initial value problem, right? And if I was going to check that this is a solution, I would differentiate this guy. If I did that, y prime would be -e to the 2t, and that would be plus 5e to the -2t. I differentiate it again, and this is a -2e to the 2t, and -10e to the -2t, right? And I add this guy, and subtract 4 of the particular solution. So this is -2e to the 2t minus 10e to the -2t, and I subtract 4 times minus 1/2 e to the 2t minus 5/2 e to the minus 2t. So I get a minus 2 here and a plus 2 here, and I wind up with a minus 10 here and a plus 10 there. So indeed, I do get 0 as required. So this up here is indeed the solution to the initial value problem up here, right here. Okay, so that is kind of an outline of what solutions might look like now for second order equations, right? We wind up with there being not just one infinite family of solutions, but 2 infinite families, right? I wind up with these linear combinations of e to the rt for 2 possibly distinct values of r. And that is what we're going to show in the next section. I think we'll go ahead and do one or two more examples